This is second half of lecture 20. We will continue talking about fluids, and we will start by looking at a very interesting application of the fluid pressure, which is hydraulic lever. Hydraulic lever schematically looks like this. It's basically very similar to the connected tube setup that we looked at in the first half. So usually you have some sort of liquid. This liquid could be oil. And in equilibrium, the liquid would be at the same level on both sides. Now I have two pistons here. One of them is wider, another one is narrower. And I can move those pistons up and down. Now we know that even though this side is much wider and this side is narrower, as long as the liquids are at the same height, you will have exactly the same pressure. So in this case of the equilibrium, when the liquid is leveled, pressure here, which I will call pressure 1, is the same as pressure here that I will call pressure 2. Now, even though the pressures are equal, the areas over which those pressures apply are obviously not equal. You have more area here. Let me call this area A2, and you have much less area over here. Let me call this area A1. Now, if pressures are equal, if P1 is equal to P2, then just to remind you, pressure is force over area. So it's F1 divided by A1. And this is equal to F2 divided by A2. So if pressure is equal, it follows that you could apply small force where there is small area, and you would get much larger force where you have larger area. And that's because the ratio of small number to a small number is the same as this large number over this large number. So in this specific case, if I apply some force F1, then something that's rested on this side will experience a much larger force, which is from here. I can derive my force 2. My force 2 will be force 1, A2 divided by A1. So I kind of have this enhancement of my force by the factor of the ratio of the two areas. And this is how we are able to, by using hydraulic levers, lift very heavy things by applying not as much force. So now one question that you may be having is that, why is this possible? Are we cheating physics? Are we somehow breaking something like conservation of energy? And the answer is that we're not really cheating physics, but it is true that there are always trade-offs. You cannot just get something out of nothing. You have to gain something, you have to pay something. And in this case, what's happening is that if you think really carefully about this, if I want to move this weight, let's say I have a weight here, if I want to move it by, let's say, 1 centimeter, this means that my oil must go up by 1 centimeter, which means that I have to fill this volume in, and the volume is 1 centimeter in height and whatever the cross section was here. And to move that much oil from this side, I would have to move this piston by much larger distance than 1 centimeter. So if the ratio of areas is 1 to 5, then to move this side by 1 centimeter, I would have to move this side by 5 centimeters. And that's when I would have expelled enough oil here to fill in all the space and to move my weight by 1 centimeter. So even though I get away with applying less force, I have to apply that force for a longer distance. So I basically have to do exactly the same work. I don't win in how much work I can do, but I win in what's the maximum force that I have to apply. So hydraulic levers don't magically give you extra energy, but if there is a limit to how much force you can exert at a given time, they can do that. You can trade your force for distance. And sometimes some of the jobs that are impossible without this become possible with hydraulic levers. Okay, so what I want to talk about now is kind of a very important concept when it comes to fluids, is the concept of buoyancy. And to introduce this concept of buoyancy, I would like us to think about some fluid. It could be water. And I would like us to think about what happens when an object, some sort of object, it could be a spherical object, is submerged into this liquid. So you cannot submerge things into rigid bodies, but you can, since liquids don't conserve volume, you can submerge other objects into liquids. And so I have the sphere submerged. Because it's in the liquid, this liquid will apply, the molecules of the liquid will collide with the object. Because of those collisions, there will be some pressure exerted. And I know that if I'm near Earth's surface, unless I'm in space, I get more pressure as I go deeper. So, pressure over here will be equal to pressure over there from left and right. But pressure from below will be slightly more than pressure from above. Okay, so the difference between these two pressures will be rho times G times H, where rho is the density of my fluid and H is the height difference between these 2 points. And so if, from left and from right, I have same pressures, but from below I have more pressure, it follows from here that, that there will be a net force acting on this object, and this net force will be pointing up. And it, kind of almost doesn't matter. It doesn't matter what kind of shape this object has. No matter what kind of shape it has, it could be a cube. There will always be a lower side, and you will have more pressure there, and you will always have a force, a net force pointing up. And this is the so-called buoyant force. Now, what does buoyant force do? It pushes up, so it kind of makes, in some sense, objects lighter when they are submerged into fluids. And the buoyant force, I don't want to do derivation here, but the buoyant force turns out to be equal to the density of fluid times the volume of the object that's submerged times G. Which is probably not surprising given this formula. The pressure difference depends on rho, depends on G, depends on H. And the buoyant force turns out to be equal to density of the fluid times volume of the object times G. This is our key formula. I will circle it in red because I will be using it later. And one thing that you probably noticed is that, again, here, the buoyant force doesn't really depend on shape. If you have two objects, they could have different shapes, but as long as they have the same volume, they will experience the same buoyant force. And this formula, if you look at this formula, you have density of the fluid here, you have volume of the object here. And if you think about this, the volume of the object is the volume of the water that this object displaced. Yeah, so this is also volume of the displaced fluid. And now if you multiply density of the fluid by volume of displaced fluid, density times volume is mass. So you will get mass of the displaced fluid times G. And the mass of the displaced fluid times G is the weight of the displaced fluid. So one way to think about this, to think about buoyant force, is you can think about the water that was here, and then this water got displaced, it moved up, and it's kind of, you know, as a toy model in your head, you can think about buoyant force as that displaced water pushing down, trying to get back to its original position. Now, there are a few kind of gotcha questions that we sometimes ask students. And so one question is, let's say I have water, and so in this cup, I will put something that's floating. I don't know, I will put a basketball in here, and I will just hold it with my hand so that it doesn't float. And here I will put a bowling ball of the same size. And now I don't really have to hold it because the bowling ball will just sink. And the question is, which object experiences more buoyant force? Is it the basketball, or is it the bowling ball? And you know, the intuitive and wrong answer is that sometimes you kind of want to say that it's the basketball that experiences more buoyant force, because this bowling ball sank while basketball kind of wants to float, so it feels like it experiences more buoyant force. That if you look at the formula, the buoyant force is density times volume times G. And so since they are both in water, and since they both have the same volume, the buoyant force is exactly the same. So this buoyant force is equal to that buoyant force. And the only difference, between the behavior of these two objects is that even though these objects experience the same buoyant force, the bowling ball experiences more gravitational force, and that's why it sinks. So if you think about this basketball here, this basketball experiences gravitational force mg. It also experiences buoyant force FB, and this is rho of water times the volume times G, and this force is rho of basketball times volume of the basketball times G. Same thing for the bowling ball. So the buoyant force is the same, rho of water volume times G. Gravity is rho of bowling ball times volume times G. So even though buoyant force is the same, since density of the bowling ball is higher, mg here overcomes the buoyant force, while mg here cannot overcome the buoyant force. So now I want to move to slide number 8. And I want to talk a little bit about floating versus sinking. So I want you to imagine that we have this glass filled with water, and we have an object, and we're slowly submerging this object into water. So this object could be on a rope, hanging on a rope, and we're slowly lowering this rope into water. So let's think about what happens here. Just before we start submerging it, the object experiences gravity, mg, and tension, and those two forces are balanced. Because we're not moving, let's say we're not moving this object with acceleration, we're just slowly moving it with constant velocity. And now if I partially submerge this object into water, it will displace some amount of water, and now it will start experiencing a third force. So the first force is mg, mg didn't change. The second force is tension. And the third force is the buoyant force, which is pointing up. And this buoyant force is equal to density of water times volume submerged times g. And so let me rewrite this mg as density of the object times volume of the object times g. Now, in the equilibrium, these forces must be balanced. So the buoyant force plus tension must be equal to mg. So tension must be equal to mg minus buoyant force. And if I make these substitutions, I will get density of the object times volume of the object minus density of water times volume submerged times g is equal to tension. So there will be less tension in the rope, of course, because buoyant force kind of partially helps. Now, if I fully submerge my object, let's say I fully submerge it, then what happens is that this volume right here, volume submerged, is equal to the total volume. So I will get, as my tension, I will get, now I have the same volume, I can take it outside of my brackets, I will get density of the object minus density of water times the volume of the object times g. And so now, depending on how these densities compare, I could be in one of the three situations. If my object is denser than water, so if rho object is more than rho water, then this will be some positive number. And this tells me that I have less tension than I would have, but I still have some tension. Okay, I still need some force to keep this object here. And if I were to cut this rope, then there would be no tension. There would not be enough buoyancy to keep the weight, and this object would sink. So if density of the object is more than density of the liquid, I will sink. If density of the object is exactly equal to the density of the liquid, then my tension will be 0, which means that I don't really need any forces to keep this object here. And this means that my object is kind of freely floating. It can be at equilibrium in the middle of this liquid. But if my density is less than density of water, then my tension force will turn out to be negative. And this actually tells me that not only do I not require tension in the rope to keep this object, it's the opposite. There is more force pushing up than pushing down. And in this case, the object will just move up because there is the balance of forces is broken. It will move up. It will partially emerge from this fluid. So when it partially emerges from this fluid, we get back to this equation. And it will stop when the buoyant force, which gets weaker as you have less and less of the object submerged, until that buoyant force equilibrates with the weight, with the mg. So if this is the case, if density of my object is less than density of the fluid, I have floating, my object will float, and exactly how much of the object is submerged underwater will be dictated by this equation. I will have exactly as much underwater as required to cancel the force of gravity. So again, if you have questions, if some of this is not clear, please join us Wednesday and Friday, 12:30 to 2:30. So what I want to do now is I want to go over 2 problems in the textbook that have to do with buoyancy. Hopefully, those problems will be instructive enough and they will help you with the rest of the homework. So the first question is about an alligator. You have this alligator submerged into water, and the alligator has this funny shape where its head, which is shaped as a rectangular prism, is above the water, and the rest of its body is below. I'm told that the mass of this alligator is 130 kilos, and that the this surface is 0.2 square meters. And now the question is, if this alligator swallows some stones, which increase its mass by 1%, how far would it sink? So I think it's clear that if this alligator swallows stones, it will become denser because its mass changes while its volume doesn't. And if it becomes denser, then it will have to sink further because it will need more buoyant force to keep it afloat. Okay, so now let's first think about what's happening before this alligator swallows the stones. Before the alligator swallows the stones, there is a downward force, which is 130 times 10 mg, about 1300 newtons. And there must be an upwards force, which is a buoyant force, which is density of water times volume of the alligator submerged times g. I know that density of water is about 1,000 kilos per cubic meter. So my buoyant force is 1,000 times volume submerged times g. So from here, it looks like I can actually compute my volume submerged. My volume, since these two forces must be equal, my buoyant force must be equal to my gravitational force. So the volume submerged is this divided by 10,000. This is 0.13 cubic meters. Now, what happens if I increase my weight by 1%? So if I increase my weight by 1%, my new mass is 130 times 1.01, which is 131.3 kilos. So then my gravitational force mg will also increase. It will become 131.3 times 10, which is 1,313 newtons. And now I will need more volume to be submerged to have more buoyant force. So my new buoyant force will be rho, density of water, times volume nu submerged, times g. And these two forces will have to be equal. So 1,313 will be equal to 1,000 times volume nu submerged times g. And my new volume from here will be 0.1313 cubic meters. So you see how this is more than that, which makes sense. I became heavier, so more of me is underwater now. Now let's compute the difference in the volume. So difference in the volume is new minus old, and it's 0.0013. So this is by how much my volume has changed. And now let's think about how high does this volume extend. So I have rectangular prism here. To get submerged by this much more volume, my volume is surface area times height. So surface area is 0.2, 0.2 times h must be equal to this. From here, I can find my h. H is 0.013 divided by 0.2. And I get 0.0065. So this many meters, or 0.65 centimeters. Okay, now let's look at problem 20.2. In problem 20.2, this is again about buoyancy. I have some, what do I have? I have water. And in this water, I have a wood block. This is not a very good drawing, but I think you get the idea. A wood block. And the mass of this block, they tell me, is 3.67 kilos. And the density is 600 kilos per cubic meter. This wooden block is fitted with lead, and lead has density of 1.14, 10 to the 4 kilograms per cubic meter. It's obviously denser than the wood. And they tell me that 0.9 of its volume, so 90% of its volume is submerged underwater. The question is, I have to find the lead mass, if it's fitted to the block's top and if it's fitted to the block's bottom. So what I will do is I will solve only one of those cases when lead is on the top, and I will leave it up to you to solve the second case when the lead is on the bottom. So I have this lead here on top, and 90% of my wooden block I know is submerged underwater. So let's think about this from the point of view of the wooden block. What kind of forces does the wooden block experience? It experiences several forces. One force is its own weight, so mass of wood times G. A second force is the normal force from above, from the lead plate. And the third force is the buoyant force pointing up. I believe these are all the forces. So I get my M of wood times G is equal to the buoyant force plus normal force. Now let's think about this normal force. What's the normal force? Well, if you think about it from the point of view of the lead plate, this lead experiences two forces. One is the normal force from the wood. Another one is mass times gravity of the lead. So the normal force must be equal to mass of lead times gravity. So I will write that here. Mass of wood times G is buoyant force plus mass of lead times G. Now, what can I say about the buoyant force? I know that 90% of wood's volume is underwater. So the buoyant force is density of water times 0.9 of whatever the volume of the wood is times G plus mass of lead times G. Okay, so this is my equation. I will look at this equation and I will think about what to do with it. So the first thing that I will do is I will cancel out G because it looks like I have G everywhere, so it cancels out. And now I get this equation. Mass of wood is mass of 0.9 times density of water times volume of the wood plus mass of lead. So what do I know from here? I know mass of my wood block, it's 3.67. I know density of water is 1,000. And volume of the wood, I don't know. So this volume remains unknown. And mass of the lead, I also don't know. I know its density, but I don't know its mass. Okay, so I have this equation, but in this equation I have two unknowns. So basically what I have to find is this. I have to find the mass of the lead. But I have a second unknown, which is volume of the wooden block. So I have to think about what to do with this volume. Now, if you look into this problem, there is a second number that we have here that we haven't used yet. This is density of wood. And so if I know mass of my wood and if I know density of my wood, it should be pretty straightforward to find volume of my wood. It's 3.67 plus equal to 1000 times 0.9. And volume is, so density is mass divided by volume. Volume is mass divided by density. Mass of this wooden block is 3.67. Density is 600. So 3.67 divided by 600 is my volume. Plus mass of lead. And from here, it's pretty simple to find mass of lead. It's 3.67 minus 3.67. And what do I have here? I have 1000 times 0.9 divided by 600. So that's 900 divided by 600. And as I'm looking at this equation, I kind of don't like it because I see that 900 divided by 600 is, what is it? It's 3 halves, so it's 1.5. So from here, I'm getting a negative number. And I don't like this because my mass cannot be negative number. So what I will do is, since I don't like what I'm getting, I will go back and I will see where I made a mistake. And if you notice this mistake while I was talking, well done. And I think my mistake was here. Basically here, I wrote that a mass of wooden block times G is equal to the buoyant force plus normal force. This is wrong. My normal force is in the same direction as my weight, so this normal force should be over here. This normal force should be over here. And now when I move this normal force on the other side, it will acquire a minus sign. So this should be a minus sign. This is a minus sign. This here is a minus sign. This here is a minus sign. This is a minus sign. And now, now I will get exactly the same thing, but reversed. I will, if I solve this equation, I will get 1.5 times 3.67 minus 3.67, which is 0.5 times 3.767, which is 1.835. So my lead weighs 1.835 kilos. Okay, so you do part B, and the difference in part B is that now this lead is on the bottom, so it is already submerged in water. You will have to add a second buoyant force, which is the buoyant force on this piece of lead. Okay, so I didn't want to re-record this, even though I made a mistake, because I think this is very instructive. This shows you how important it is to, when you get your result, to think about it and to think whether or not it makes sense. This is a very useful, very fail-proof way of finding random mistakes in your work. Okay, that's all for lecture 20. Thank you very much for your attention. And again, if something is unclear, and it will always be when you learn something for the first time, join our help room Wednesday, Friday, Monday, 12:30 to 2:30. Feel free to ask any questions that you may have about these lectures or homework or anything else.